All right. Good morning, everybody. So today, welcome to our today's session for AI for All initiative. For the spring break, actually, our schedule was a little bit messed up, but to make it to the mainstream, we are having a lecture today. So today's lecture is about Chinook detail. What can we do at UAF HPC cluster? And once again, the speaker is Kevin Galloway, the system admin at RCS, Research Computing System. So Kevin, please feel free to share your screen and start your lecture. And right, let's see if I can. So you do not need to do any board work, right?
No.
Let's see if I can.
Let me get this shared real quick. Okay. All right. So this lecture is kind of Chinook in depth, what you can do on Chinook's HPC cluster in particular. Mainly covering what we have installed, how you can get software on there, and using programs and package managers like Conda and other software installs. Good.
Did they start recording? That's what I have to check.
Yeah. Okay. So this one's going to be kind of a grab bag of topics. So first off, we'll talk about what modules are available on Chinook, and how you can find maybe modules that we've installed that might pertain to your area of science, what your research is trying to do. I'll talk a little bit about Jupyter Notebooks, open on demand, how that works, and how you can install your own kernels into that. Talk a little bit about building software, both how we build software, some of the options that are available to other HPC centers that try to make building scientific software easier. We'll chat a little bit about containers, how you use them, why they're used, kind of the advantages and some of the disadvantages of containerization. And I'll talk a little bit about where you'd use a VM in comparison to a container. I'll talk a little bit about kind of some more advanced Slurm topics to kind of make your workflows when you're submitting jobs a little bit easier, and how that can be combined with kind of user interfaces that you create to submit jobs. And finally, I'll just talk very briefly about kind of the RCS rates and what other services we provide that might help with sharing data, accessing data, and things of that nature. So to start off with, why do we build software on these HPC clusters? The main reason we try to build kind of a centralized source of software is that we have many groups who are using the same tools. Because we're affiliated with the Geophysical Institute here, a lot of it is focused on kind of earth sciences and a lot of bioinformatics. So we have a bunch of software that we've built that these groups can use because they're using the same tools. If you're trying to look for certain pieces of software, like you just don't know what we have installed and you don't want to look through every package, there is a flag you can pass to the module command called key that will allow you to look for certain keywords in package module description, software descriptions, to kind of show what's available. So you can do like module key bio, and anything that has bio in its description will pop up. Or if you're looking for certain libraries like image libraries or things like that. One thing I'll note on Chinook in particular is a lot of the system or dependency modules, things like shared libraries, Bison, Flex, things like that, we have defaulted to hidden. This means when you do like a module avail, they won't show up. We mainly did this because these modules are mostly important to people who are like compiling their own software, who are trying to build their own software, not using like a package manager or anything like that. So we just hid those to keep them out of the way. If you need to find them, you can pass the show hidden flag to the module command, and those will show up. And I'll show some examples of that later on. Uh, because we use a tool called EasyBuild to build our modules, we make use of what are called tool chains. Tool chain is basically a compiler, a math library, a version of MPI, and a couple other core modules that a lot of software needs. And so a tool chain will have all of these of a certain version in there. And as you build other software, it will use this tool chain, like this same version of the compiler, this same version of MPI, and this same version of like a math library to build all the software to it. This just makes it easier to standardize what versions are available. And we try to follow, with a little bit of delay, easy builds kind of philosophy for their tool chains. They update twice a year. They're moving to a faster one. I'll talk a little bit about that later. Our two main tool chains are the FOSS, the FOSS, which is the free open source. This will be your like GCC compilers, OpenMPI, like OpenBlaz for your math library. And the version we're using is the 2022A version that EasyBuild provides. It's GCC Core 11.3, if that's important to you. And then our other tool chain is the Intel tool chain. This one's slightly newer because we had a couple of researchers who needed just a newer version of Intel. This is the 2023A. I don't recall the exact version of Intel that's on it. I can look that up later. But this has the Intel compilers, Intel's math library, the Intel MPI. As for our kind of general groups of software that we have kind of like three big ones. The first one is we have a fair amount of bioinformatics software installed. This is stuff like SAM tools, Blast Plus, Augustus. These tend to be slightly older versions, mainly in a lot of HPC centers. The centralized software install usually lags a little bit behind the release schedule just because people, when they're working on HPC for their research, like reproducibility. And so if they have to update their libraries and recompile their code or redo their workflows every time, it can be sometimes hard to compare results run to run, for one matter. And then two, a lot of people will get their workflow up and running. It's working well enough. It's working fast enough for them, and having to like rebuild their tool chain in the future to use newer software might have enough of a lag that it's just easier to stay on a single version. We try to get around this by when we install newer versions, we let them coexist side by side. We have a fair amount of like file formats and file operation software, stuff like libtiff, libpng, netcdf, hdf5. Most of these are kind of centered around climatology and earth sciences. So the big file formats that we have software to really interact with are going to fall under those categories. Finally, we have just a lot of earth sciences and geospatial software, stuff like Ferret, GDAL, CDO. Again, that's just kind of our bread and butter because we're part of the Geophysical Institute. If you're working in a group with a fairly large amount of people who need the same sort of software, please let us know here at RCS and we can build software for you that you can all share. And generally, we're okay with even building newer versions. Like if you're working on stuff and then a year later you need a newer version of like SAM tools, we're happy to build it. The main thing that we try to have users or researchers focus on is if there's updates like every few months, we'll probably try to leave that in the hands of researchers just because they can get to it faster than we can. So now say we don't provide the software that you need and you're the only person that needs it. So we'll help you build it, maybe even build it as a software, but it's going to be a lower priority for us. So you decide that you want to build it by hand. The first thing that I want to point out is no user will ever get sudo or administrator access on our machines. I only really bring this up because a lot of tutorials assume that you're going to be building their software on your own personal machine. So they'll have commands in there that are like sudo apt-get install, MPI, or sudo dnf install MPI. If you try to run that on Chinook, we're going to get an email that says that you tried to do something you weren't supposed to do. Um, Generally not a huge deal. We'll look at it, see what you tried to do, and kind of laugh it off. And if we see someone like keep trying this sudo command, we'll reach out and try to let them know what they're doing and how to actually build it on Chinook. Another thing that I also wanted to mention is you get better performance as well if you kind of build from source using what's installed on the system rather than either copying a binary or getting it from a package manager, because you can make use of all the CPU architecture features. You are using stuff that was also built using the CPU architecture features best suited for the system itself. Um, Another thing that you don't run into if you're building stuff by source is you don't run into issues where someone built a library, a piece of software like an executable using specific shared libraries that then you have to try to match. Um, we run into that a few times. There are a couple other ways besides building it yourself that you can get around this, like containers that I'll get to in a little bit. So you've decided that you need to build or install this software by hand. How can you do this? The first is that you can just build it by hand manually. This could be, running your code through a compiler, GCC mycode.c-o my program. This could be through make files, something with like configure make, or using something like automake, cmake, any of those kind of build frameworks. These can sometimes be pretty easy to do. Other times, they give you just so many options that it can be very confusing, and making sure that you're pointing your make file, your configure script, all of that to the right directories can be a little difficult. So what else can you do? If you want to go kind of a step up, a couple of universities have created different sort of build frameworks. These tend to be more targeted toward system administrators who have to build a lot of scientific software, but they also allow users, individual researchers, to build software themselves. So the University of Ghent has built a framework called EasyBuild, which was really made for reproducibility, and it's supposed to really be for building scientific software for system administrators in kind of a shared setting. As they've developed things further, they've given a little bit more access to individual users where you can build software in like your own home directories, your own directories that you're pointed to. The other big one has come out of, I think it's University of Texas. Is maybe wrong on that one, but I'm pretty sure it's that. And that one is SPAC. This one is made more to act like a traditional kind of package manager. So if you're familiar with like apt or yum, SPAC will be pretty familiar. It's made more for kind of ease of use, and is a little bit more developer focused. So if you're a developer building a bunch of software, SPAC really makes it easy to create like a little package script that will allow you to build whatever scientific software you either wrote yourself or that you're trying to get built on things, using a variety of dependencies. We here at RCS have more familiarity with Easy Build since that's what we were using. We were really using that before SPAC became a thing. But most US-based institution nowadays, maybe not most, but a lot, have been moving towards SPAC just because it's a little bit easier to use. And then finally, there are just the package managers. Some of these are, library specific. language specific. Others might have a little bit more flexibility. These are things like Conda, pip, things like that. So I'll talk a little bit about Easy Build first. It's kind of this build framework. It's written in Python. The current version needs, I think, Python newer than 3.6. Older versions can use like Python 2, but hopefully no one is using that nowadays. Easy Build is kind of broken down into a few different kind of core concepts. The first is tool chains, which is kind of the list of baseline software included to build a whole bunch of other software. These can go from as kind of low level as like, this is the version of the GCC core that we're using, up until, the higher level tool chains of this is the compiler we're using, this is the MPI we're using, this is the math library, etc. Are we using CUDA or not? They update their tool chains roughly twice a year. So they have an A and a B version. As they're moving forward, they're discussing, and I think they're implementing more regular updates. I think they're trying to go to quarterly next and just prefacing it by year, month, because that's just kind of what a lot of software does. So the tool chains, the kind of nice thing about the tool chains is, you're going to be locked into certain versions of everything. So if you know that you're using, FOSS 2022A, you're going to know what like the exact version of MPI you're using, the exact version of like the GCC compilers you're using, etc. And you only know that you're going to be using newer stuff when you go to like 2023A. The next thing is all the build information for a particular software package tends to be in what's called an easy config. This is actually just like valid Python, like a valid Python file, but it's mainly just a bunch of dictionaries and lists in there that just say, these are my like build dependencies. I need these other easy build, easy configs or software installed to build my software. And these are my dependencies, like the shared libraries that I need. One of the powerful things you can do with Easy Build is these can be either other bits of software that you've built with Easy Build. So if you've built like, let's say the zlib libraries with Easy Build, your dependency can point directly to that. Or if you just want to use your system version, you can specifically say, hey, I need zlib, I want the system version, look in userlib. These easy configs can also have various tests in there, like, hey, I know that this is fully built because these files exist. Run a sanity check, make sure, when I build Python that there is a Python executable here, or there's these shared libraries that I need. Because of this, easy configs can range from pretty simple, like just a list of dependencies and a test for making sure like a binary exists, to really complicated if you're needing to like have a bunch of different build dependencies and then actual dependencies and then a bunch of sanity checks. Because this is also written in Python, you can write valid Python in here to make your like sanity checks as complicated as you need. The next part of Easy Build is what's called an easy block. This is actually just some Python code that runs actual build steps. So in a lot of this, it'll have portions in there that's, hey, extract this tar.gz, place it here, go to the directory, run configure with these flags, and then run the make command to build it, and then make install to move it to where it's supposed to go. The Easy Build framework has a lot of community-driven easy configs and easy blocks, so you don't need to write a lot yourself. And for a lot of common build styles, like using configure make or installing something with pip, they'll already have an easy block created for you. And there's a bunch of easy configs for various pieces of software. Kind of the downside to using Easy Build is, one, it can get very complicated with the sheer amount of easy configs and easy blocks that you need. And then also, if you're trying to write one from scratch, there can be a whole lot of information that you need or might not think about. And then these are just some of the commands that you can do. As EasyBuild has kind of matured, they've moved from just having everything in a couple of repos. So there's like an easy configs repo and an easy build, easy blocks repo for them. You can also search these now through the easy build command, which is just this EB. So you can do like EB dash dash search file name dash file names, and then search for a file name. Will show you what easy configs are available to you. You can fetch the source code with this like fetch flag. One of the important ones is this dash dash show config flag. This will show you what your easy build configuration is, like where it wants to install software, where it wants to actually build software, where the modules will reside, and things like that. I should also mention easy build is aware of what module system you're using, like if you set it. So if you're using lmod, it will write its module files in the lmod format. If you're using the TCL Tickle modules, it will write it in that format. And then also, when you're using EasyBuild to build something, it knows what has also already been installed with EasyBuild. If your configuration set up, so it won't try to like rebuild everything every time unless you like force it to. And if you actually want to build something, you pass it the dash lowercase r flag, EB. You can pass it this robot path. That just says this is where my easy build, easy config files are. This is specifically if you just want to keep, a smaller set of easy configs, or you just want to know the ones that you have installed, so you're not pulling it from the repo automatically. You're not pulling it from easy build's library directly. You can just pass a directory to it. And then you say, okay, this is the path to my EB, my easy config file. If you do the dash capital D flag at the end, that tries to do a dry run, which will say, hey, this is what I need to install. These are all the dependencies. You might need to pass it a show all nowadays for show this full list of dependencies, but it'll show you what's going to be installed and what doesn't need to be installed. And then you do the lowercase r to actually do the installation. Next is SPAC. This is also written in Python. Their main configuration file, if you're like looking to build software yourself, like if you're trying to add your scientific software to SPAC, is this package.py file. This holds all the different versions that are available, all the different dependencies it needs, and you can add in certain flags in this file. So when you're using like SPAC install, you can pass it flags. This can be stuff like, build with MPI, don't build with MPI. It needs only these dependencies. This one's an optional dependency. It can be as flexible and complicated as you want. So SPAC tends to be very flexible with dependencies, which EasyBuild is not for the most part. And you can, like, for example, you can specify, I want my dependencies to also be built with SPAC. So when you install it, SPAC will install all your dependencies and then what you're trying to build. Or if you already have a bunch of stuff installed on the system, like a compiler, GCC, you can just say, hey, use what's already on the system. I don't, need latest and greatest, just use what's there. Some of the commands with SPAC, you can do SPAC list package name. This will list all the packages that have package name in it somewhere. So if you're like looking for, PyTorch or something like that, you can do SPAC list PyTorch and it will show you everything that's there. You can do SPAC info package name, and this will show you all the information about that package, like what versions are available, what the dependencies are, a brief description, and if there are any variants. And variants tend to be things like, this is built with MPI, this is built with GPU support, and things like that. And then if you want to install it, you do SPAC install package name, and then you can pass different variants, different flags. So you can do like SPAC install package name at a version, which will install it with that specific version. Or if you do like SPAC install package name %sign dependencies, it will build that package with those specific dependencies. There's a whole lot of other things you can do here. You can like omit certain versions, omit certain dependencies. It's a very flexible and very powerful tool if you know what you're doing. It's something we're looking into just because we sometimes get users who need to build software. They don't want to use like a Conda environment or something like that. But we're still learning about this tool, but I wanted to let people know that it's out there because it's a lot easier for users and developers to use than Easy Build. And finally, we have kind of the package manager thing, package managers for installation. Some are included and or very closely linked with compilers or interpreters. For example, R, Julia, Python to an extent have their own package managers that are either baseline of the language or borderline baseline. So it might be a library like pip, you do pip install package name. If you're building it for yourself, you need to pass it this -- user flag. That'll put it in your home directory. Otherwise, it will try to install it in like system wide, and you're not going to be able to do that on the HPC. Otherwise, you might be able to install it as part of your compiler or as your program. So like R, for example, you have this install.packages package name, which will look for the package that you're trying to install. If it doesn't exist, it will try to install it. And then R by default, if it's not installed and you haven't said specifically where to install it, it will ask you in an interactive manner where you want to install it. It'll default to someplace in your home directory. Julia works pretty similar. You have to import the package module, then you do like package.install to do it. And so these are some ways if you want to just use kind of baseline things without getting kind of the heavier lift of like a Conda or another package manager. But sometimes you might need a variety of software that isn't just related to a specific language. In that case, you might want to use one of these other package managers of stuff like Conda, which I'll talk a little bit about shortly. There's Homebrew and npm for Node that is kind of straddles that line in between like language manager and extra stuff. But both Homebrew and Conda can install a wide variety of software. They might be Conda is kind of focused on Python, but it will also add in binaries and other libraries of other languages. One big example would be like MPI. It will pull in some MPI libraries. Or if you install like netcdf with Conda, it will pull in some C and Fortran bindings. Brew is also made for specific users. This you can install a whole lot of things with it, OpenMPI, specific packages. Generally, you see Brew more on like your laptop or something like that, but we have had a couple of users who've used it on Chinook. So since Conda is the big one that we see that people really want to use, I'll focus a little bit on that specifically. You might hear of a couple different versions of Conda: Anaconda, Mini Conda, Mini Forge, and it can get a little bit confusing of what is what. Conda is the actual package manager, and then that was provided by a company as part of their Python distribution called Anaconda. They eventually open sourced Conda in general, and then other groups made use of it. Mini Conda is the lighter version of Anaconda that the Anaconda company provides. There's been a little bit of a shift away from Mini Conda and Anaconda specifically due to some licensing changes they made that I think they backtracked, but because they made those changes, people are kind of a little wary of that. And then there's this Mini Forge. So Mini Forge was developed by the maintainers of the Conda Forge library. So when you install Conda, you have a couple of channels that you get your software from. The Conda and Mini Conda default one is just the Conda channel, which Anaconda runs. And so they made a license change that was kind of a little stricter than it was in the past for educational institutes. So You can still use mini conda, but if you don't want to use that conda channel, which has some restrictions on it, you can use the conda forge channel, and you have to just change that in your in one of the config files. Miniforge kind of came out and was like, hey, we'll just create our own conda implementation that just defaults to this conda forge. The important part for us, for RCS, the reason we recommend it over using miniconda is it includes this other dependency solver package manager bit called Mamba. Mamba is a lot faster to install software than Conda is, and it is orders of magnitude faster. Generally, if you're installing stuff that's complicated with a lot of dependencies. For whatever reason, Conda's dependency solver can get really slow once you've installed a lot of software. And it might be a side effect of running it on like a network file system. But for whatever reason, we've noticed Mamba acts much, much faster. Just to give some ballpark numbers, on one of our systems, we had a shared Conda environment that we had installed using Conda. And after a few years, and it did have a fair bit of software in it, but I didn't think anything overwhelming. It would take like 6 to 8 hours to do the dependency solver and then actually start installing it. Mamba took maybe like half an hour to an hour tops. So for us, it's much faster. So between it using this sort of free open source channel by default and including this Mamba package manager in it, that's what RCS recommends. And then once you actually get MiniForge Conda, MiniConda installed, you generally do this through an install script that you download from their site. It will modify your RC files to kind of initialize your environment, so it knows to, when you're running like your Python, it knows to use its base environment, and when you're trying to install stuff, it knows to use directories and executables in your own directory that you have access, read-write access to. Couple links here for actually installing MiniForge and also using Mamba to install. And as I mentioned before, as part of the install, you'll be asked to initialize Conda. It says something like, proceed with initialization. We recommend just saying yes, then you'll have to like log in and back out or restart your shell. If you want to create an environment, you do Mamba or Conda create-n, the name of your environment, and then whatever packages you want to install. And then you can do Mamba or Conda activate name of your environment. You can mix Conda and pip. We generally don't recommend doing that because Conda can start being confused. So we recommend, like, if you say need a newer version of Python than what's installed, but you just want to use pip for everything, you can use Conda to create your newer Python install, but just use pip. Otherwise, try to just use Conda. One special note is in the previous lecture, we showed that you can use Jupyter Notebook through Open On Demand. Here are the instructions for actually setting up a kernel. So if you wanted to get like GPU libraries in there, like PyTorch, these are the steps to do it. So the first thing, and we're looking to see if there's a better way where you can do this all through Open On Demand. But the way that I know works is either on Chinook 04 or chinookgpu.alaska.edu. If you're using GPU stuff, log into chinookgpu.alaska.edu. If you're just using CPU, go to Chinook 04. Once you're there, you want to load the FOSS 2022A module. Then you'll load the Jupyter Lab module, because this Jupyter Lab module is what our Open On Demand instance uses to spin up your Jupyter Notebook. I'm currently looking into ways where you can run Jupyter Lab from your own environment. If you install Jupyter Lab in like your environment and have that loaded by default, it might work, but there's a couple caveats that I'm still working out, but that is our next step. But for now, if we recommend just using the Jupyter Lab one. You do module load CUDA if you're on the GPU node, just to make sure you get the CUDA libraries in there. And then you run python-m ipykernel install --user, the name of your environment, and then just the display name. This will create that kernel, and then everything else you can then do in Open On Demand. You can then select the kernel in Open On Demand, and that's where you can start installing software through the Jupyter Notebook interface. So that's kind of a nice option if you need to get additional library. And I'll show a demo of that. Well, I'll show a demo of selecting the kernel in Open On Demand and installing additional software.
One quick question
Yeah.
before you switch to this container.
Yeah.
So all these SPAC or Easy Build or Conda, are they all available as a module in on Chinook that whenever I will log in and then if I type module load
not
Conda,
yet.
something?
So Easy Build you can install in your own Python environment.
Okay.
It's just something you can install through pip. And then SPAC you can pull from their GitHub. Building modules though is probably a good idea. We'll look into doing that.
Okay.
But yeah, at the moment it's just we recommend if people want to build it in their own Python environment or pull the SPAC repo
Okay.
and then install it that way.
Okay. So, and another question would be like, well, so when we are installing these installer packages like this Conda or SPAC or anything, where do you suggest to install those packages? Because I know that if you install Conda, it will automatically take like 5 gigabytes of space or something like that.
Yeah.
So what is the suggestion?
So kind of unfortunately, it's still the home directory. So you have 50 gigs, so you can't have too many environments there. If you are like having a shared project, like you have, 2, 3, 4 people going to be using the same environment, what we recommend is emailing us at RCS, and we'll create you a directory in what is it? User local unsupported. It's called unsupported because we'll help you build stuff there, but we won't maintain it. That's going to be left to the user. We recommend that people install shared environments in there. You just have to email us. We'll create you a little directory. And we keep an eye on how big that gets. We understand that Conda environments are getting larger and larger. So, 10, 15, 20 gigs. But if you're building like, 30 Conda environments, we'll talk to you about trying to find a better solution for that. What we absolutely do not recommend is building it in your Center One or in the future your BGFS directory because Conda specifically uses a lot of small files. So when you're loading something or trying to run Conda and it's having to read or write all these really tiny files, it can bog down the entire file system. So absolutely do not put your Conda environments in the shared file systems. One other method that we've sort of recommended is if you do need like, say, 5 different environments, but you're only using them like one at a time, you can archive part of your environment and then load it back out, but that's kind of advanced power user stuff. If you are interested in that, we can kind of show you how to do that. It'll mostly consist of like tarring up each of your individual environments, copying them to archive, deleting them from your home directory, and then pulling them back out. It's clunky, it's not the best. We are looking into a couple other options for kind of more shared or project space, but we're just need to get some other file systems up and running before we can do that. Other centers sometimes do have like a shared project space, and we're kind of hoping to eventually get there.
Yeah. So here is the second question. So is it like well, yeah, I understood that you are recommending to install it on my home directory as a. So now assume that I am a PI for a Chinook project.
Yep.
And I have like 4 or 5 students are working with me. So is it possible for me to create a shared environment for all the students? I mean, and do I need to talk to you or?
Yeah, you talk to us and we create the directory. We can do that really quickly.
Okay.
And then what we would do is we give you ownership of the directory. And then when you set up your Conda environment, I think you can put, so there's one of two ways to do it. Like one, when you originally initialize Conda or Mamba, my mini forge, it'll ask you where you want to put your environment. So when you're initializing it, like installing it for the first time, you can point it to that directory. Otherwise, I think there's a -- prefix flag that will install the environment where you tell it to. And so that's kind of the important part, because one of the kind of annoying things about Conda is it hard codes. Maybe they've changed it, but at least a few years ago, they hard coded the path to your Python in there. So if you like built it in your home directory and then tried to copy it somewhere else, it would still try to run everything from your home directory, which can run into permission issues. But this also brings up maybe something that I'll talk about. I'll talk with the group at RCS to see maybe if we want to come up with a way to have more of a shared space for this sort of stuff, because we are seeing more and more groups that are trying to share.
That's the current thing that I am trying to understand. So if I need anything for any environment, programming environment, share across the folks, share across a group, I first should communicate with you, right?
Yeah.
I mean, rather than trying it by myself. You can do it much faster than me. That's what I'm asking. So what is the best way? Because when a scientist will work, I don't know about much about the RCS system admin stuff or something like that. So I have a requirement for shared environment. So what is the best step for me?
So the best step would be to contact us first, because the first thing we need to do is create like the shared directory for you.
Awesome.
And then from there we can discuss, like, if you just need to share a Conda environment with your group, we can send you the commands to run and let you handle that. If it's something that's maybe a little bit more complicated, we can maybe take a little bit more of a hand in it. So yeah, contact us. We'll either get you commands that you need to run that then we'll let you run, or if it's something that we need to do, we'll get that set up for you.
Awesome. Great. Thank you.
Get back on track. One of the other kind of ways to run software is through the use of a container. If you've seen a lot of like NVIDIA stuff, they try to provide a lot of tools through their NVIDIA NGC something containers. And so this is what's called a form of virtualization. So basically it tries to package the essential operating system bits into a single image that then you can kind of run on another system. It's kind of a lighter weight version of a virtual machine. Once your container is created, it's immutable. You can't really modify it without kind of rebuilding it. There's some caveats there depending on what containerization tool you're using, and how you're like layering your file systems and stuff. But generally, once you build your container, it's built and it just sits there. You're not going to run an update on that container and then plop it back down. Another thing about containers, depending on how they're used, is they're supposed to be kind of destructible, not super unique with a bunch of customizations in it that you need to set up each time you run it. In the cloud world, you'll hear you should run your containers like cattle, not pets, which basically means you want to be able to spin up a container and shut it down and not have to like worry about rerunning that exact same container and it has some sort of state in there. The reason containers are used is they're portable and reproducible. There's this asterisk here because there's a lot of research in how reproducible results-wise running stuff on containers are. If you build a container and run it on one system and then run it on another system that has, different underlying hardware, you're like, how similar is that? Or even just different versions of base software, even if it's running the same hardware. One other thing about the portability is that the version of MPI on the base system needs to be what's called like ABI compatible with the version in the container. Generally, if you have like open MPI installed at the base OS, most MPI versions will work inside your container. But this is really just kind of a long-winded way of saying using MPI with containers can get a little finicky. Some common tools that you'll see for running containers. The big one for a while is Docker, but this is not really used on HPC systems. Part of this is because the way Docker worked in the past, so they've slowly pivoted, is everything needed administrator root access to run Docker. And if you're trying to let your researchers use that, you do not, no offense, want to give all your researchers root access. It's just really easy to accidentally do something that affects other people's work. So the ones that are mainly used on HPC systems are Podman, which is like Red Hat's containerization. Originally, it was also kind of like Docker, where it needed admin access, but they've been moving back a little bit to allow users to just run their stuff. They've been putting a lot more focus on that. And one of the upsides to using Podman is they alias a lot of the Docker commands. So if you're familiar with Docker, Podman's pretty easy to pick up. The other big one, and this one was developed specifically for HPC, is Apptainer / Singularity. Basically, it was originally Singularity, then the company kind of split into the free open source version, Apptainer, and another version, Singularity, and they've kind of diverged. RCS has Apptainer installed, and this is pretty easy to use. Their containers are what's put into what's called a SIF file, an SIF, and you just basically run that like almost any other program. And then finally, another one that's come out and has slowly been gaining in popularity is Charlie Cloud. Can't remember which university this came out of, but they wanted a faster way to spin up containers and having it all happen in user space. So when you build a Apptainer or Singularity container, you do need root access, so you can't build that container specifically on Chinook. You can pull containers from like NVIDIA or Docker. That's fine. But if you need to like build one from scratch, you're going to have to do it on your machine and then copy over the resulting container to Chinook. Charlie Cloud allows users to build their container. It doesn't need any root access. So if you're on an HPC system with Charlie Cloud, you can build your container there. It's something we're looking into, but for the moment, we're sticking with Apptainer. As mentioned, HPC centers typically use Apptainer or Podman. And the main use cases for containers in the HPC world is either complicated builds, like you're building something like, in the old days, it was TensorFlow, or I forget the name of the other big one. Sorry, lost it. PyTorch to a degree, or a lot of these giant like kind of parallel programs that need a lot of dependencies. It was a lot easier to build that in a container where you had admin access to your container to like just install the libraries yourself without having to build a bunch of libraries by hand like you'd have to do on an HPC center. And then a lot of these also expect libraries to be in like user lib instead of another one. So like for these big ones, it was really easy to just build it in a container and then use that on your HPC center. Or the other reason is portability. If you're working in multiple HPC centers, you might not want to have to like rebuild your giant software stack each time, or you might run into, HPC Center A has, GCC 14.4 and HPC Center B is still on like 10.3. You don't want to have to like constantly rebuild your software because of that. If you have a container, you can, just move this container from center to center. The other reason is due to glibc. So one of the base underlying libraries in most Linux installs is glibc. This is used to build a lot of the core components. So switching this out can be difficult. It's a little bit easier nowadays to have multiple versions. of glibc, but back in the old days, if you didn't get your paths set up quite correctly or how you're running your software correctly, you could make your entire shell unusable until you relogged in. So the place you mainly see this actually is with Conda environments. Conda will install some pre-built executables in some of their packages. And sometimes those are built on a much newer OS than what an HPC center has. One of the I don't want to really say it's a downside, but one of the challenges that HPC centers kind of run into is it can be hard to update your OS to like major versions, just because people in the middle of using your HPC cluster, you don't want to stop their work. They're using a bunch of software that was built specifically for a version of an OS. So sometimes this glibc can lag, particularly in Red Hat derived OSs, because they use a pretty conservative glibc when they update. So what we would find, depending on how far that gap got, Conda would be using a newer version of glibc that wasn't supported on our system. You run into issues, containers can solve this. On the flip side too, if you have like your software stack was built on like an old version of an OS, and you need those specific libraries and stuff that's too new doesn't work, you might be able to build a container to run your old stuff and then run that on an HPC. The big thing that's going on right now in the HPC world is trying to bridge this gap between the traditional HPC structure of, you have some code you want to run, you submit it to a job scheduler and run it, with the sort of cloud-based system, which and most of the major centers kind of assume that you have unlimited resources where you want to request a bunch of containers run, and it just goes to the cloud and gives you these resources. So there's a lot of work into trying to bridge this so you can have kind of this cloud-based workflow work on an HPC system, or still allowing your traditional HPC to work. The big project that does this at the moment is called Slinky. It's made by Slurm, and it's supposed to kind of allow you to run cloud workflows on an HPC system while keeping track of like fair share and scheduling and all that. This is something that we're still looking into. We're still very kind of traditional HPC cluster, but we're kind of looking into kind of this next generation, since a lot of vendors are kind of going towards this cloud first mentality. So RCS uses Aptainer. You rarely use Aptainer interactively after you've kind of built your container. You usually do like Aptainer run container, Aptainer exec, and I'll show an exec example if we have time. Container, then whatever command you're running. It's compatible with most Docker and other containers. If you want to pull something from like a Docker container, just do Aptainer pull Docker : // and then the URL and then the version. Like for example, if I wanted this PyTorch from NVIDIA. If you're using the GPUs, you do need to pass it this --NV flag. It just sets up some of the drivers and some of the mount points, like the dev NVIDIA mount points, to be able to run. And then you can kind of set this up in a couple of ways. If you know that you have like a container that just runs a specific workflow, like you have a container that just runs training for an LLM, and it has like the same inputs, same outputs, you can set this up as you build it as part of its run script. So when you run Aptainer run, train llm.sif, it will just run those sets of commands that's in its run list and just run. Alternatively, say you wanted to set up a container that has certain Python libraries in it, but you're going to be running a bunch of different scripts with it. You do Aptainer exec, your container, and then whatever command you want to run after it. It can just be kind of useful if you're doing, usually for like programming environments and things like that. And finally, there are Um, so containers are kind of lightweight virtual machines. Virtual machine is basically a virtualized version of an actual server. And you might want to know when you'd use a virtual machine versus a container. Generally, since this acts as sort of a normal server, a normal computer, you'll want to use it if you have like a program that has like a GUI component to it that you don't want to run like directly on a login node. Like might need dedicated resources to it. Or if you have some sort of interface that you want to write that can interact with the HPC system. So say Slurm has a REST API where you can submit jobs or get information through the REST API. You might want a virtual machine, like a server, that will actually communicate with Slurm through this API, and you can do all sorts of stuff with it. So say you're doing wildfire research and you have like a model you can run on specific areas. Maybe you design a GUI where it has like a map of, say, like Alaska, and you can highlight a portion of Alaska, and it will take all the data that it has for that region and then submit a job that runs some analysis on that data. Virtual machine would be good for something like that versus a container. There's some kind of blurry lines in between, like when to use a container, when to use a virtual machine, because containers can do this, but because a virtual machine acts as like an actual system, it's a lot easier, we find, for like researchers and developers to like interactively work on things without having to like rebuild containers and things like that. The other big thing with virtual machines is that it's mutable. So any changes you make in the virtual machine will stick around. That can be pretty powerful as you're like building your interfaces, or if you like even need to like pivot a little bit. You're like, hey, we have a nice interface that works, and oh, we can add this other function to it without having to like say rebuild a container or decide that you need to run two different containers. So um, those are kind of the sort of different use cases for it. Um, RCS does offer virtual machine infrastructure if you need one. There's like a subsidized tier for like a slow VM, and then paid tiers for more powerful VMs. The other big part for virtual machines too is if you're just sharing data like with outside collaborators, you just need some sort of sharing interface. Virtual machines pretty useful for that. We have a lot of systems that do that. And I think the last bit here is kind of what I'm calling advanced Slurm. Um, Slurm can be kind of as powerful or as simple as you want it to be. One of the tools that you can use for Slurm for your workflows are what are called job dependencies. And basically, you can launch different jobs based on conditions that you tell Slurm. So you might have one where these are just some examples of it, but the kind of interesting ones here, for example, would be like passes as like dependency equals these flags. But if you do like after not okay and then a job ID, so say you have like an analysis that you're running or like some sort of training or something, and you launch that job, you can launch a job after it that's called like, failed cleanup or something, or cleanup after fail, where if you put this after not okay, the job ID of your training job, if that job fails, and so you just need to clean up all the data there, this job will only run if that job fails, and then you can in this like cleanup job, um, you can delete all the bad data because the training maybe went sideways or the job didn't finish. Um, and then there's like an after okay where only run this job if the other one completed successfully. This one can be useful if you have like a data transfer job. So you have a job that like downloads a bunch of data that your next job actually needs, and you want to kind of separate those. You can just say, hey, yeah, after that other one completes, run this. And I have a brief example of that in a moment. And then there's this singleton job, which this job will only execute after all jobs with the same name and user have ended. This can be kind of good for like to run after if you're running like multiple batches of jobs or something like that. So you might have this one run after all the other of the jobs of the same type have run, and this just like sends out a blast that like either like reduces everything, like your results into like one file, or notifies you that everything's finished. The other bit of Slurm that can get a little bit that can be a little bit useful is Slurm has a whole bunch of environment variables. They start with slurm underscore. And the two that we kind of think are pretty useful are the slurm node list, which if you echo this like environment variable, it will tell you what nodes your job's running on. And this can be useful if like you see something weird with your job, like it's running slower than usual or it errored out with a weird error. If we have the node list, we can see if there's issues with those nodes, like maybe some old processes didn't get cleared up, or we had one example where when you're running with Intel MPI, if we were running on two different Intel architectures, MPI didn't work. And that one was kind of hard to figure out because just when we were doing our tests, we were happening to run on nodes that were compatible, whereas the researcher was running on two incompatible nodes. The Slurm submit directory environment variable is also pretty useful, just where your job was launched from. If you're using like relative paths or something, you can maybe see why like files weren't found. And then if you're using MPI, there's two different ways you can run it. We kind of recommend using the srun way nowadays, but you can either run, your MPI run, MPI exec commands, like normal MPI run -n, your program, or you can just use srun-n, and then either the number of paths that you need, and then your executable, and Slurm knows to run it as MPI. Or if you just do like srun my executable, I think it will take all the information Slurm has and try to spread it across all the tasks it has allocated. And the final bit that I have is just a couple of our HPC rates, and I can show the full rate page as well. So this is our HPC. If you want to get HPC access, so we have three different tiers. Our tier one is our subsidized tier, is what we call it. It's open to all the UA research community, free for UA faculty and staff. The asterisk after staff is that generally PI needs to have some sort of purchasing authority. So generally it's faculty who tend to be the PI on it, but if a staff member can find someone to be PI, that's good. Your home quota, for no matter what tier you're on, outside of maybe tier 3, is just your 50 gigs. And then your center 1 quota is 1 terabyte per project in the subsidized tier. Or tier 2 is if you've purchased a node. RCS works on what's called a community condo model. We have a bunch of nodes that we've purchased with our own money that are available to everybody. And then researchers can write into their grants or if they just have deep pockets and feel like gifting nodes, they can purchase a node that gets added to the cluster, and they get access to longer runtimes and higher priorities. Our compute nodes, just compute, run $13,000 to $15,000 right now, just because of the AI boom. Stuff's got more expensive. GPU nodes, those get very, very expensive nowadays. So if you're interested in that, let us know. We'll pull quotes. And there's another kind of caveat to a lot of the vendors we work with try to have a much faster turnaround now because they're trying to lock in their prices before stuff goes up too. So it's kind of a complicated time right now to be buying hardware. Then your center 1 quota in this tier 2 is you get your subsidized 1 terabyte and then an additional terabyte per node that you purchased. I have these asterisks here because we're moving to a BGFS file system as well. This BGFS file system, it's a parallel file system, still running benchmarks to compare the speeds, but should be comparable or faster to center 1. But there's more space available, so it's going to be like 3 terabytes for the subsidized, and we haven't completely locked in on the number of terabytes you get per node, but I think at the moment it's like 3 terabytes per node. Then we have this special like tier 3 project. This is if you need dedicated HPC resources. So say you need to spin up your own little cluster for whatever reason, basically contact us. We'll get you quotes on how much it would cost. And then you can set up how much storage, quotas, etc., that your users get. The big example we have of this is we have a cluster called Athena that's for a specific project for a geodata cooperative. It's just its own separate cluster that we purchased, and we just worked with them. Kind of a lesser version of this is if you just have an individual server that you want to buy too. That's one of the things we offer on our service rates. But basically, you pay the cost of the hardware, a work authorization for like 40 hours for us to install, set it up for you, and then there is a yearly fee for maintenance and all that. We have a couple groups that have made use of this because they just needed like a machine for their lab or something like that, but that is also an option if you don't need the full cluster. On the storage side, this is just the HPC storage. We offer other storage options. Subsidized free. It's about 15 if you want to lease HPC storage from us. It's about 15 cents per gigabyte per year, which equals about $150 per terabyte per year. Again, with the BGFS file system change, these rates will probably be tweaked, but we'll probably have those ready in FY26. If you just want to purchase storage, it's basically the price of hardware plus a 40-hour work off. And then from year 2 onward, it kind of breaks down to $5, $2.50, or $1.25 per raw terabyte per year for basically maintenance. This is so like if you have a whole bunch of disk, you're not kind of penalized for having a bunch of raw data. But if you're like trying to give us just like, oh, I want you to maintain a server with a terabyte of space, that's a lot of work for a terabyte of data. I think that's all I have on the slide thing. I can show a couple of demos unless there's any questions.
This is great. I mean, these RCS rates and all these things. I mean, I believe many people are asking me for like funding and proposal writing and all these things, and they're looking for some sort of rate. So that's great.
Okay.
That you included in this presentation. Awesome.
Yeah. And actually, let me go to our web page. The other two things that might be useful is we have a facilities statement. If you need to basically describe what our data center is like, what we do. I know a couple grants do that. That's just here on the website. Then we have our full service rates, like our online storage, offline, and the virtual machine if you're interested in that as well, and our Linux server support. Those are other options. We have a couple of like bioinformatics users that decided just to buy their own server because they had specific needs and stuff like that. So I guess the first demo I will show will be our using a different kernel in Open on Demand. So a Jupyter Notebook on the L40Ss. Launch that. And so I've already run that ipy kernel create command to create a new kernel. I'm going to have here in my Open and on Demand session. What's this? Oh, there it goes. And so when I go to start up a new notebook, you'll see I have this kind of list of kernels over here. So I have this kernel demo. It should spin up this interface, and I've installed PyTorch in here already, so I can do like torch and then torch.cuda.is available. And if this is all set up correctly, this should say once it runs, stuff is available. Oh, maybe I need to print that. Yep, there we go. And you can see that, it has torch in there. If I wanted to install something else, I can install it through the Jupyter notebook. I'm pretty sure. Let me see if pip works. I'll just say like matplotlib, run, and hopefully it will. Yep. So once you have your kernel installed, you can run all your pip commands through the Jupyter notebook and get stuff installed. One note is you do have to restart the kernel usually once stuff's installed. But now I should be able to like import matplotlib down here. Let's do import matplotlib. And hopefully that imports. Yeah, it didn't error out. So it's pretty handy to be able to do things that way. And then the other demo that I'll show is just a kind of one of the advanced Slurm things. Let me stop sharing real quick and make sure I get the right directory. Share this again. Okay, so I have a little script here called job.sh, and this is going to be using the dependencies that I talked about. One of the kind of unfortunate things is you do need to do a little bit of bash scripting for this to work kind of dynamically. So if you have like a whole set of jobs that you want to run one right after the other, you can do it that way. But basically what this is doing is it's launching one job, my file transfer job, which is located in this directory. And this is just something that waits for 10 seconds, not actually transferring any files. And then afterwards, I do an sbatch. Oh, and then it saves the output of this, which will be just the job ID in an environment variable that I can then throw this dependency equals after OK job ID. And then I run my analysis. So if I run this job-sh, you'll see that it submitted a batch job. If I do an SQ, let's do that. You'll see that I have my transfer job running. I have an analysis job that's waiting because the transfer job hasn't happened. And now because that transfer job is done, the analysis job has launched. That's one of the kind of the powerful things about using job dependencies. And then the last thing that I'll show is basically how to run a container. And actually, let me show module key real quick. So if I'm looking for like bio modules that are installed, like new module key bio, and it will list anything that kind of has bio or is labeled as a biology program. So I have this PyTorch container, and I have a little small torch job. So if I wanted to like run this on here, let's say I'm like, oh, do I have torch installed? I could try to run this check GPUs, and it'll error out because I don't have torch. If I wanted to run this locally, I can just run this apptainer bind, and this should have torch and tell me that I don't have any GPUs because I'm on Chinook 2. And here we just have that apptainer, you do exec, you pass it your flags. Here I'm having to bind a directory so it can find my Python script, my check GPUs. You might also need to bind directories for like your libraries or whatnot. And then if I wanted to like run this on the GPU node, I could do this apptainer and do like srun dash pl40s dash GPUs equals 4. I think this should just run. You'll see that it found the NVIDIA SMI. You'll get this thing about too many bind mounts, but that's fine. And you'll see because I asked for 4 GPUs, it was able to successfully run PyTorch, and it is able to find all 4 of my GPUs. But yeah, so that's kind of the in-depth look into Chinook, kind of what we have, a little bit more of kind of the power user tools, but I think that's all I have unless there's any questions.
That was a great presentation. And so I have a quick question about the compatibility between Docker and Aptainer. Most of the container that are running on Docker, did you find any issue? I mean,
so in our tests, not really. Like this container that I just ran is actually a Docker container, and it ran fine. I think this just has PyTorch installed though. In Python, but generally we haven't found too many issues. The one thing that we have kind of found that's a little bit harder to do with with Aptainer is a couple of tutorials that we found. They're like, hey, download this container, and then you run like Docker interactively. Those sometimes have a little bit of issues.
I see.
Just because I think they mount stuff in a different way. And they have like file systems embedded, whereas with Aptainer, you have to make sure that you bind mount them correctly.
And the other question is like, well, let's assume that I have installed an app utilizing Aptainer or Conda or anything. Can I utilize it on my Open On Demand account? So, or is there any issue?
So,
or do I need to install the same way utilizing PEEP that you showed now?
Yeah. So, at the moment, if you're trying to install stuff in a Python environment, you'll have to do it the way I showed you with the IPy kernel to get it to work in the Jupyter notebook. If you're doing stuff on like the terminal interface in Open On Demand, generally it shouldn't really matter as long as you're submitting stuff to the right partition. The only place it gets a little iffy, and this is something that is next on my list to add to Open On Demand, is if you're doing GPU stuff, unfortunately, you still need to log directly into the GPU login node, Chinook gpu.alaska.edu, just because if you're like installing Conda stuff for it will sometimes not work because of the different CPUs that are on our compute nodes, which is Intel, and our GPU nodes, which are AMD. Yeah. But I'm working on some instructions to see if we can get Conda environments to run in the Jupyter Notebook interface of Open On Demand. I just haven't cracked it quite yet.
Okay, perfect. And yeah, the other question would be, do you already have some sort of like instruction to get started with Open On Demand on your website yet?
Not yet. It's kind of next on our list. Because right now our on-demand instance is in
experimental.
Yeah, kind of in an experimental beta phase. I mean, if you want access to it, email us and we'll add you. But one of the things before we do our full release is getting documentation up. So that's definitely on our list to do.
Awesome, great. So yeah, I mean, I think that's all from my side, and yeah, that's it. Thank you.
And as always, if anyone has any further questions, or if you watch this in the future and are like, hey, what's going on? Feel free to email us at uaf-rcs@alaska.edu, and we'll try to answer as best we can.
Okay, thanks, Kevin, for the wonderful lecture. So once again, the recorded material will be available on our Data AI Lab website, which is cs.uaf.edu/data-ai-lab, and just click on the courses and workshop, and then click on this thumbnail of AI for All initiative, and the recorded lecture will be available here with all the materials that Kevin shared today, including the PowerPoints and everything. So feel free to take a look, and if you have any question on the webinar or on Kevin's talk or anything, feel free to reach out to us, either myself or Kevin or anyone. And thank you. So let me stop recording.